Okay, so when last we met, we were just starting to introduce this concept of electric field. So when we talk about electric field, it is around this charged particle, and we see the interaction of the fields. Now, we saw the little demonstration where we saw the forces interacting, and we saw the field lines interacting, okay? So we saw that the field lines were what caused that attractive and repulsive force between the two charges. And you'll get to play around with this a little bit in the lab on this unit. So we already talked about this, but when you saw the picture of the positive and the negative charge, you saw that the electric field for a positive charge points outward, and the electric field for a negative charge points inward. Now, if we have different shapes of a conglomeration of charges, those field lines are going to be a little more complicated, but always for a net positive, they point outward, and for a negative, they point inward. The more lines there are around an object, that implies a stronger field, and then the fields will weaken the further you get away. Field lines have to be single valued in space, so they can link up if they're pointing in the same direction, but they can't be in opposite directions. They'll cancel out. Okay, so we saw already this visualization of why. Now we can see why opposites attract and likes repel. So when we talk about field, like we had our two charges, what makes it simpler to figure out what's going on is if we identify the thing that we're going to look at the force on and the thing causing the field. So two separate things. We say the thing that's causing the field is the source, and we say the thing feeling the force is the test. Okay, so the source will be the thing that we're going to solve for its field, and then we're going to forget about it. Then we're going to take that field and see how that affects the test charge to create the force that we're interested in. So we can separate out those two from the Coulomb's law equation. The source's field is all over, okay? So no matter where I am, I'm going to feel the effect of that field. Even if it's just little bitty, I'm going to feel that effect. Now, yes, I know my test charge also has a field, but I don't care about it. I only care about the source's field and how it's affecting the test charge, all right? So I'm going to ignore the fact that I could solve for the field of the test charge for right now. Now, the electric field is a vector, okay? It points outward or it points inward. So we have to figure out which way it's pointing so we know how it affects the test charge. So how much force is going to depend on two things. The first thing is, how big is the test charge? What is its magnitude? The other thing is it's going to depend on its sign. The direction of the force is going to depend on the relationship between the sign of the charge and the direction of the field. The amount of the force is going to depend on the magnitude of the charge. So once we know that, we know the number, but then is it plus or minus is going to depend on what is the relationship between the charge and the field. And it's not just as simple, oh, a negative charge is going to have a negative force. It's not that simple. It's going to depend upon what is the interaction between that field and that test charge. Okay, so we already mentioned that the field lines point outward or inward depending on the sign. So the simple expression that we can write down is the force is going to be the product of the test charge times the electric field. Now that's the magnitude of it. The direction is I'm going to have to look at the interaction between the sign of the charge and the direction of the field lines. So I need to know both of those. So what that means is I don't need to put the negative sign in if the test charge is negative in this formula. I don't need to make Q naught, which stands for the test charge, negative. So this is the test charge's value, magnitude, times the strength of the field, magnitude. So if I go back to my Coulomb's law formula with this, I can write down the electric field of a point charge. So I just cancel out the test charge, basically, is what I do. And I'm left with the magnitude of the electric field is KQ over R squared. So the magnitude is the number, and then the direction, I figure out if it's a plus charge for the field is pointing outward from the charge. If it's negative, it's pointing inward. And so I have to figure out where I am in space as to whether that is a negative X or a plus Y or whatever it is. And you'll see that as we work through the problems on this. Now, if I have a whole lot of charges, I might have a sheet of charge. So if I have a whole bunch of charges, normally I would do calculus, but it turns out for something called a capacitor, which is two sheets of charge, one is plus and one is minus, it's actually fairly simple to write down the electric field if you do calculus, because it's a constant. It's a constant between the sheets. Okay, so if you do the calculus, what you get is the charge of one charge, which we'll call, or the sheet, which we'll call Q, doesn't matter if it's plus or minus, we just use the magnitude, divided by that epsilon naught constant, that permittivity constant, and the surface area of the sheet. So Q over epsilon naught A, all of which are constants. Sometimes you'll see Q over A, which is charge per area, written as a sigma, which is a surface charge density. So sometimes you'll see it written that way also in some books. That just means the total charge divided by the total area, which is uniform. It's uniformly charged. And this makes something called a capacitor, which we're going to talk a lot about in a later part of this unit. So capacitors are useful because they store charges. They store charge and they store electrical energy. They're like an electrical suitcase, if you want to think about them that way. Now, in this unit, we're going to consider a situation called electrostatics. Electrostatics means the charges don't move. Once they get on the balloon or once they get on the sweater or whatever, they stay there. They don't flow. So we're not talking about current flow. And so it's really important for this unit to understand that if something is not moving, that means it's not experiencing an acceleration. Okay, that was one of the conditions of equilibrium, is no acceleration. So in this case, the charges are stationary, but if we talk about like a metal ball, for example, which is a conductor, remember the property of the conductor says that the electrons are able to move around in the bulk of that material. So if I had a metal ball that had fields, electric fields inside of it, electric fields cause forces, and forces cause accelerations, and then that would get rid of my static situation because then I'd have a bunch of charges moving around. So what has to happen inside a conductor is something has to happen to cause those charges or those fields to cancel out inside that metal. So what happens is we get distribution of charge around the conductor that causes the fields inside the metal to cancel out. Okay, so what will happen is charges will move to surfaces. They'll move either to the outer surface of the conductor, or if there's a hollow place inside the conductor, they'll move onto the surface of that inner hollow area. And what that does is they line up in such a way that it causes their fields to cancel. So that way, inside the metal, there's no field, so there's no acceleration, so I don't break my rule of charges experiencing an acceleration and no electrostatic situation. So anytime you have a static electric field on a conductor, if there's any extra charges on it, I know they're going to be either on the inner surface of a cavity or the outer surface of the conductor, or sometimes both, depending on what we need. Okay, so that's the first set of notes. And we'll stop the recording there, and then we'll come back and pick up about potential.